Okay, so good afternoon. I hope you guys were able to have a restful weekend. Today, we're continuing at NMR spectroscopy. We're finishing up the introduction and then we'll start the fun stuff. I've uploaded the tutorial for this online. Did I upload these lecture notes? I don't think so. But I did. I don't think so. So lecture 12, NMR spectroscopy. Now we're going to be dealing with a bit more shielding effects, all right? So in the previous class, we spoke about when you expose a nuclide to a magnetic field, it precesses, meaning that it spins on its head like a gig when exposed to magnetic field, right? Now the effect of the electrons surrounding the nucleus on the resonance process of the s electrons, this splitters circle around the nucleus. So remember, the s electron, once closest to the nucleus, will have its greatest effect on whether it's shielded or de-shielded. Because as the electrons also spin, it generates a current. Now, if the magnetic field is generating a field, radiation field, that pointing in one direction, and as it's exposed and the electrons are spinning, there's also going to generate a current or another magnetic field in an other direction. It can either align with the magnetic field or go against the magnetic field. And whether it reinforces or takes away from magnetic field affects whether it's shielded or not. Okay. So moving electrons, it gives us a current. The current induces a secondary magnetic field, which opposes the primary magnetic field. Following me so far? Now the field experienced by the nucleus is going to be the effective magnetic field. So you have the one that is coming off from the instrument plus the secondary magnetic field that is opposed from the electrons moving around. The s electrons that is the closest around the nucleus as it spins. All right. So you have the effective magnetic field that is experienced, where sigma is a shielding parameter. Now this looks very familiar when you learn Z effective, but you'd have had something else here. All right. Now for resonance, we can actually vary the frequency of the radiation, so we can have the effective equal to the frequency of the whole spinning process. Now you can say increasing electron density around the nucleus gives you a better shielding, means that it builds up electron density, it goes against the magnetic field and shields it. All right. High E density, high secondary magnetic field, low effective magnetic field felt by that nuclei. All right. So as one increases, the other one decreases. So as this contribution gets higher, the overall value of this decreases. That makes sense? Okay. Now the opposite is also true. Decreasing electron density around the nucleus results in de-shielding because this contribution also gets lower. As this contribution gets lower, the effective magnetic field is going to be stronger. All right. Now, the proton nuclei in different electronic environments processes or spins at a different rate. Remember, as it's in a different electronic environment, meaning if it's near electron donating group, electron withdrawing group, the proton will spin at a different rate. Does that make sense to you? So you can actually calculate the frequency using this equation. Now the carbon 13 nuclei is in a different, it also functions the same way. In different electronic environments, it processes, meaning that it spins at a different frequency depending on the environment that it's in. Now let's look on this. For example, the electronegativity will vary. So carbon is less electronegative than nitrogen, which is less than oxygen. So look what's happening. So the de-shielding of the methyl groups and the hydrogens on the carbon as you move from left to right. So as you increase the electronegativity of the atom, you expect that the frequency at which they spin to increase or decrease. Increase, right? Means it's going to get higher. Does that make sense to you? I'm saying that as you increase electron negativity of the atom that is attached to, it's the more de-shielded it will be. So it's going to precess or it's going to spin at a higher frequency. Increase electronegativity of the atom it's attached to. Because you're removing electron density away from it. Remember, that means the overall effective, remember, you know, the frequency in which it processes or precesses, that it spins, is given by this equation. B is a magnetic field experience, which would be the B effective. As this value increases, this value decreases, right? So if it becomes more de-shielded, that means it's taken away from electron density. That means the overall value, that contribution for this is going to be lower. So it's going to be higher. So you're going to expect it to rotate at a higher frequency. The magnetic field. So you have the primary magnetic field and you have the secondary magnetic field. Right. And sigma is the shielding constant associated with the nucleus. All right. So as a result of this, you know that the frequency which it precesses is directly proportional to the effective magnetic field that is felt by the nuclei. All right. Following so far? The effective, I wish somebody brought the whiteboard, but look like nobody decided to bring the whiteboard today. The effective magnetic field that is felt, it's all dependent on the environment that is in. The greater the electron density, the lower it spins. The frequency which spins because it's going to come against it. So for example, if I'm spinning you, right? You ever are, think about you're spinning, what do you call those little thing, swing something? What do you call those little thing that kids go on and just spins run around? Is merry-go-round called? Ferris wheel, that's what it's called. I feel like it's been years that goes around, like, you know, not up like this, you know, like, no, is it a merry-go-round? You have the handlebars and everything, not like, it's a merry-go-round? You sure? All right, let's say you're right, as I'm not sure. As it spins, if you put your hand out and it keeps stop, you want it to start slow down, it's the same thing with this. Think of the shielding effect as something as slowing down the effect of you spinning it. All right. So the more you're slowing it down, is the less fast or the lower frequency in which it spins. It's the same thing with this concept that we're talking about right here. Because remember, as it's exposed to magnetic field, it spins on its top and the head like a gig. You know, it spins, it rotates. All right. So achieve resonance, meaning that when you say when we talk about achieving resonance, meaning that we're going to pulsate it in such a way that it now aligns with the perpendicular magnetic field that we'll be experiencing. That is when you see resonance. So we can actually vary B until that the frequency that it spins actually equal to the frequency of the electromagnetic radiation that you're putting in. All right. Or you can keep B constant and vary the electromagnetic radiation until they're equal. So those are the two ways you can do it. Now, chemical shift. This is where things start getting a little bit fun. Well, for me, probably not for you. All right, so a complete spectrum of a compound is obtained when this equation has been satisfied for every proton nucleus that exists in the molecule. So from start to finish, I'd really appreciate if somebody go for the board, but from start to finish. All right. Has been satisfied for every nucleus in the carbon-proton NMR spectrum. Now, how many signals do you expect to observe for this compound? Meaning, how many environments that you're anticipating to see for proton NMR? Anybody can tell me? All right. This is how you do it. You look, when I say environment, what do you think I mean by environments? What's around it, right? So if we're talking about these protons right here, What's around these protons right there that I highlighted on the board, on the screen? All right. Maybe I need to be a bit more specific. What is it close to? What is adjacent to? What's it nearby? A carbonyl, right? Our carbonyl tends to be electron donating, electron withdrawing. All right? Cool. Do you see any protons near to it? It's just it by itself, right? Okay. What about this proton here? What is it adjacent to? An oxygen. All right. So if I were to put one in the underline and the one in the box, do you think they're in the same chemical environment? Which one would be more de-sheeted, do you think? The oxygen, right? Isn't that simple? No? No, you don't just tell me the answer. What was hard about it? I'm sorry? Shielding means that it remember we saw when I was doing all of this, it was falling over your head. Right. Remember, shielding has to do with the electrons that's around it. That means if you have something that pushes electron density around it, it reinforces this around the nucleus. Remember, NMR is nuclear magnetic resonance. So you're dealing with the excitation, the excitation of the nucleus. All right. So if you're decreasing electron density around the nucleus, meaning that electrons in the s orbital around the nucleus, if you're pulling that away, that means there will be less shielding effect, meaning that it's going to be de-shielded. Does that make sense? If you have electron donating group, that means it's pushing electron density on it. That means there's going to be a greater effect from the secondary magnetic field. So you should anticipate it to have a lower effective magnetic field that's experienced by the nuclei. Does that make sense? All right. I'm asking you if these protons, which one you'd expect them to be in a different environment? You guys have told me they both agree, or all agree that it's in different environments, and I asked you why. You said to me that the oxygen is more electronegative than the carbon, and I said yes. So I'm not really sure. You just said a while ago, you just say yes. We mean like, right? I'm saying which one would we expect to be more de-shielded? The one that's attached to the oxygen, because it's more electronegative. I'm sorry? Right? So you expect it to be more de-sheeted as a result. The less sheeted it will be. So you can see the more de-sheeted it becomes. No, I notice a lot of people not taking any notes. Good afternoon. And I listen, I may not put everything on the slide. Strongly recommend you guys write things down. Ask the questions and make the notes. Don't tell yourself, say, yo, I'm gonna get this when I go home. Right, but if you understand something, write it down. The quickest pen is better than the sharpest mind. The quickest pen is better than the sharpest mind. Something I learned in high school. Why am I telling you that? That's not your business. All right, so we spoke about how much proton signals are going to be, right? So you expect to see two different set of proton signals, right? All right, so two set of proton signals. How many carbon signals are you expecting? What you first thing you need to do is what? Are they in the same environment? How many carbons are in this spectrum in this compound? Oh, okay, if somebody tell me four, I'm gonna just leave. So there's four carbon, three carbons. Let me say four carbons. That's foolishness. If you just leave. So are the three carbons chemical equivalent, mean are they in the same environment? No. Okay. Which one you expect to be? All right. Would you expect this carbon and this carbon to be the same? Why? All I hear is one is what? One is alpha to a carbonyl, right? Please use those words. So alpha to a carbon, it's more de-shielded, or it's, use those words. Don't just say next to. All right. So this one is also next to, no, you can use next to, or it's attached to an oxygen. Oh, I didn't hear that. I just hear next to. So it's attached to an oxygen. This carbon is attached to an oxygen. So you'd expect it to be a different chemical shift, right? Okay. What about this carbon? Different one as well, right? So right away, you see that you have 3 signals for carbon. How many for the protons? 2. Three for the carbon, 2 for the proton. You understand that? You want me to go over it again? The signal becomes. Remember, we talk about shielding and de-shielding. So let me just go back for those who came. We spoke about the fact that when you have an electron in the s orbital, yes, I'm doing it for you guys. For the s orbital, it generates a secondary current that either, you might want to write it down. It generates a secondary current that either can oppose or reinforce the field. All right? The electrons in the s orbitals. Now, if it is, so the effective nuclear charge that is felt, effective magnetic field that is felt is given by this equation. B naught minus sigma times B naught. All right? Where sigma is a shielding particle. Now, if it is that you have a situation, the electron density is reinforcing, meaning it's opposing it, it's shielding it. That means the contribution towards this is high. There's a large amount of electron density and it's going against the overall magnetic field. The overall effective magnetic field that's felt by the nuclei will go down, and then it's going to rotate at a lower frequency, and that is said to be shielded. That's what I just basically said right here in this slide. All right. Sorry. I'm gonna say it again. Maybe I'm not saying it properly. When there's a higher multi-electron density around the nuclei, that means more electrons are spinning, and it's giving an electromagnetic field that is opposing the primary magnetic field. The effective magnetic field felt by the nuclei will go down. That means it will rotate at a lower frequency. That in itself becomes shielded. But that's what I just said up while, it's shielded. It's right here. Increasing electron density around the nucleus, shielding, high density, high second magnetic field, low effective nuclear charge. That's what I'm basically saying. But I'm just using a lot of words. Right. Because if you have a secondary magnetic field, it can either oppose it or reinforce it, don't it? All right. If you now take away that electron density away from the nuclei, wouldn't it be less there to oppose it? So it will become more, no, it won't be shielded, but more de-shielded. Okay, right. If it's pulling the electron density away from it, that means it's less shielded. It's going to be more de-shielded. So let's go back to this example now. Judith, I asked them, these protons, are they in the same environment? Meaning that are they electronic, are their polarity the same? Are they in the same electronic environments? Okay, which one do you think is more de-shielded than the other? This one or the one in the box? More de-shielded? I'm gonna ask the question another way. Is this proton closer to a more electronegative group than this proton? One with a box. Is it next to a more electronegative group than the one underlined? The one is next to, or is close to, or is attached to a more electronegative element. All right. So this will be in a different chemical environment than this proton right here. So you anticipate if they're in different chemical environments, you anticipate to see different signals. If there, you might want to write this down. If protons or carbons here in the same chemical environment, they will come up as one signal. If protons or the carbons are in the same chemical environments, they will come up as the same signal. Same chemical environment will come up as the same signal or the same chemical shift. All right. That is not on the slide. So you guys need to make notes as I talk. Environments. Same signal or chemical shift. All right. When I say signal, I mean chemical shift. Environment means that when you think about the words as you talk about English, what is around it? When I say environment, what is it surrounded by? What is adjacent to? What is neighboring it? That's what I mean by environment. All right. All right, I guess you just more practice, you'll see it. All right, so chemical shift. Now for the primary magnetic field, you get these type of field strengths. Now, the frequency in which it precesses is going to be 100 megahertz plus or minus 15 hertz for hydrogen in most organic molecules, or megahertz. But the frequency, the magnetic field strength must be this value for them to be actually resonance taking place. All right. So in commercial spectrometers, the magnetic field or the electromagnetic radiation experience, the frequency of electromagnetic radiation will vary. So you either can increase the field strength, the magnetic field strength, or you can increase the magnetic radiation of the frequency that is used. Those are the two ways. All right. Typically, the more common one is that you basically vary the magnetic field.
So why would you?
So you can get that, you want it to be something that's called resonance, meaning that it aligns it when it's exposed to the magnetic field, it rotates it. So if it's like this, it spins it. You guys didn't watch the video. Watch the video and go home. It flips the molecule on its head from being upward to slightly like this. And in that rotation, it generates a current. That's called resonance. Watch the video. Yeah, but I went through this last class. So, but it's in the video same way. As I sent the video. All right, so chemical shift. Now, we realize that the frequency in which the precess frequency, the magnetic field strength, and electromagnetic radiations are interdependent, meaning that one depends on the other, right? Now, the chemical shift defines resonance positions of nuclei in a way which is independent of the field strength and the frequency. Because the chemical shift, you might want to write this down, is the frequency of the sample nucleus minus the frequency of the reference nucleus in hertz over the spectrometer frequency. This is how you typically calculate chemical shift. And in UTC is typically represented as delta for change, and it's represented in ppm. The unit is ppm. So I could ask you, calculate the chemical shift for this compound. With all the information you're given, you should be able to do it. So if you want an example, you can look in Solomon's. There are examples in Solomon's, another textbook. I think I might upload another Pavia. It's more explicit in its explanation, and so Solomon's kind of steps it down. But read Solomon's first, because Solomon's not going to have all of this information I'm having there. It was going to jump straight to the point. But you need to understand the background. But read Solomon's first, and then I'm going to upload Pavia on the Google Drive. And you guys read Pavia to get a more in-depth on. Well, no, not doing that. But for those who choose to, you can get a more in-depth understanding about NMR. Now, for everything in science, you need to have what is called a reference. Because how are you comparing something without a reference point? All right, you need to have a reference point. So we use tetramethyl TMS as our reference point. All right. For the proton NMR, the hydrogen of TMS is usually the reference. For carbon 13 NMR, the carbons in this is usually the reference. All right. What I mean reference is made to be 0 and everything's compared in reference to that. So all the hydrogens in the TMS are one signal. You see that? Because they're all in the same environment. So they all come up as one signal. The carbons are all in the same environment. So in the carbon NMR, they'll come up as one signal. Making sense? Because they're all in the same environment. So they will all reinforce one another. When it rotates, they'll all come up, they'll all rotate and give the same frequency in the rotation. So the machine is going to detect that and give one signal. You mean based on the data? I don't reach there yet, but that's a good question. That is where the fun stuff comes in. The problem solving and piecing together of a puzzle. All right. So TMS is very volatile. They're shielded relative to the hydrogen carbons of most other organic molecules. So it's arbitrarily assigned as 0. All right. So for protons, the range is typical 0 to 20. Now I'll never give anything past 12. And carbon is 0 to 240, and I won't give anything past 200. Because carbon, the range in compounds can occur is way more expansive. But you'll see that as I start, but I'm not going up to 20. So we see past 12 and those things, they go into other elements like phosphorus. I'm not giving you guys any phosphorus. All right, so running a field sweep of the proton NMR spectrum of phenyl acetone. All right, so if I were to do a sweep of this, so in a frequency sweep method, the magnetic field is held constant, which keeps the nuclear spin energy level constant when the reference signal is swept to determine the frequency of the energy absorbed. All right. So when we're doing a sweep, we can actually look on what is happening. So when we do a sweep of this entire molecule, we got 3 signals. All right. So this one is at 2.1, 3.5, and 7.2. If you had to guess, where would you assign them? Benzene 7.2, well done, Judith. What would be the 3.5? Good. And that means the other one would have been 2.1. This proton right here. All right. What are those whats? Those are, come close. I'm telling you, I can't bring it up any higher. I tried. Why the what? Three. And I'm writing it on the screen now. 3.5, 2.1. All right. So the benzene ring would have been at 7.2. It's the most shielded, and there's a reason for that. I'll teach you that later on in the notes. 3.5 would correspond to what is this position called? The benzylic position. But alpha, you don't get away with alpha this time as well. But I'd ask you which alpha. No, so you better say benzylic position. Good. So use those type of words when you describe in the NMR. Benzylic position protons are anticipated to be at this region. Now, to be fair, there's actually a table, a list of data you need to know which proton occurs where. Because there are trends. They study these things. So they have to know the trends. You don't have to know it. To me, there's another way around getting the table and say, see, if you're practicing enough, eventually you just know it out of your head. No. The values. So example, you know where benzene typically know benzene typically between 7 and 8. Benzene positions will be a bit different. Alpha protons of carbon is typically come between 2 and 2.5. So like I can say this out of my head because I've been practicing long enough. Practice it long enough, use the values and expose yourself to the values long enough, it becomes a part of you. You don't have to look back through the data sheet. All right, so integration of the NMR spectrum. Now in the proton NMR, we can actually find out the amount of protons that are underneath each of these integrals, each of these curves, each of these signals, I should say, right? So we can take the integral, meaning we're adding up all the infinitesimal small points and get the complete area on it. The curve tells how many protons that are existing there. Now, the relative heights, so you should write this down. The relative heights of the integral line gives the relative areas of the peaks and thus relative numbers of the hydrogen. So this is basically saying the taller the peaks, the more protons there are. All right. Now heights and the heights are very useful information. If you see an NMR and it's very tall, it tells you there's a lot of proton there. It also can imply symmetry in the molecule. It can also imply the number of protons there. All right. The heights, the integration, all these are useful information and clues in what is really going on. You don't need to know the numbers now. There's just the same spectrum. All right. So effect of chemical environment. We spoke about electronegativity. So let's look on the example now. This is a methoxy. This is methylamine, and this is a normal carbon hydrogen bond, right? Let's call it a part of ethane or something. Look on the ppm, look on the chemical shift that's experienced. When it's attached on oxygen, the proton NMR is 3.3. But for the nitrogen, the proton NMR is 2.3. And for the carbon, it's 0.9. You see that? Look on the chemical shifts for the carbon. 55, 35, 18. You see electronegativity makes a difference. All right. Now, hybridization also makes a difference. The change in hybridization, what is writing this down? Hybridization makes a difference. The 3p orbitals and 1s orbital here, 4 sp3 orbitals. Each sp3 orbitals has 25% of a s character, means it's further away from the nucleus, and 75% of a p character. All right. Just sp3. Now, hydrogen with sp3 carbon with no electronegative groups typically come up between 0 and 2.5. sp3 carbons with no electronegative groups, the hydrogens on them come up between 0 and 2.5. Hydrogen attached to sp3 carbons with no electronegative groups resonate between 0 and 2.5. Hydrogen atoms, sp3 carbons, and no electronegative groups attached typically resonate between 0 and 2.5. It's on the screen. I didn't change it right there. Now, this is important that you know this. That means that if it falls outside the range, something is going on. So you have to think like that. If it falls outside the regular range, something is happening. It's near something. It's next door to something. You have to think like that. Hybridization, continue. So let's look at what is going on with the sp2. Now it has a 33% S character. Look how it changes though. This same proton move from 0.9 to 5.0 by just changing the hybridization state. So it becomes more what? Is it shielded or de-shielded? De-shielded. Good. I can move on? No? So which part again? Is it become more shielded or de-shielded? And the protons, if I change the hybridization state of this from ethane to ethene, the chemical shift move from 0.9 to 5.0. Is it become more shielded or de-shielded? And the answer was de-shielded. It's now resonating. It's precessing at a different frequency, a higher frequency. So it's more de-shielded. All right. Now you have other things to think about. Acidic protons and proton exchange bonding in NMR. This is also useful information. So acidic protons in organic compounds are OH, NH, and SH. Acidic protons in organic compounds are OH, NH, and SH. Acidic protons in organic compounds are OH, NH, and SH. These are sometimes called active hydrogens. Relatively easy to remove, meaning that it's labile and often involved in hydrogen bonding. Now, these are important to know because if you see something that says exchange with D2O or broad singlet, they usually come up as a broad singlet. I'll explain what a singlet is soon. As a broad singlet, it typically indicates that there's a heteroatom there. All right. That already gives you some idea of what the type you're doing. So if you're dealing with an alcohol, it affects how you think versus if you're dealing with an amine. Does that make sense to you? If I should do what? I said if it's an alcohol, it's different if you're dealing with an amine. That part? And it affects how you think. Because I could give a question like this. I could give you a synthesis question. Or I could give you the NMR. I said, based on the compound that you produced in the previous question, synthesize this from benzene. I could do something like that. Ain't that fun? I could give you a compound to solve. When you solve that compound, that's part one of a question. The next part, synthesize this from benzene. Or synthesize from this carbonyl system. You understand? Or I could have given you the synthesis of it and I asked you, okay, predict the NMR or which NMR matches this compound. I could do that as well because they're all interconnected. Now I could give you a compound. After you made a compound, I said the compound that you made, predict the NMR of the structure. Give reasons for your answers. You understand? You don't learn it yet. Obviously, I'm going to give you some tutorial questions, right? Yeah, this is tutorials on Friday. We didn't do any tutorial last week. All right, so that's a good question. Yes, OH are typically not acidic, but I'm talking alcohols, but because the interaction with the solvent is just so easy, it can be lost very readily. All right, so in these type of solvents, it can be acidic, but in general, no, it's not acidic. You understand what I'm saying? So what deuterated solvent, but I don't reach there yet. You guys are asking excellent questions, but I don't reach there yet. That's the next slide. So they depend on the rate of hydrogen bonding is the rate of the chemical exchange. I'm going to show what I'm talking about. So during the given time period, such an oxygen like OH may be attracted to several different molecules. The rate of chemical exchange depends on the pH, the temperature, and the dilution. So the more of the solvent you have, it can affect how well it exchanges. The pH is there, it can affect how fast it exchanges. The temperature they do, because sometimes you do NMR at, let's say, we typically do it here 22 degrees, but people have done it up to 50 degrees. All right? And it makes a difference. So compound at 25 degrees don't look the same as compound at 50. So here's an example now, right? So methanol, this is chloroform, right? The D is deuterium with TMS in the spectrum. So the TMS would have been this. All right? Now the 3.42 would have been the OCH3. Look on the OH, a broad singlet, right? Now, if I gave you guys a signal at 3.97 broad singlet, immediately tells you that it's either a OH, a NH, or SH. You see why that information was important? And if it's a OH, it could have been either an alcohol, a phenol, or carboxylic acid. So this gives you ideas to think about your molecule. Making a little bit more sense now? So every data, don't throw it away. It makes sense and it's for a reason. All right. Now the methanol in pure form with TMS, add 1 drop of D2O and shake it, because now there's more of the hydrogen to go around, less of the deuterium. It actually causes the peak to sharpen up. So the XD bonds stronger than the XH bonds, as I equal 1 for deuterium. So the NMR signal for deuterium not observed with the instrument set up for HNMR. We can detect the OH, the NH, SH using this technique. So meaning that it disrupts that bonding with the solvent. It rather bond with the deuterium. So that means this involvement, this exchange, it stops. So it comes out as a normal singlet. So if you ever see a broad singlet, you're not going to do this, but typically, if you're, because I've done this before, I had a compound that I wasn't sure if it was really the OH that is there, and I ran over the sample with deuterium. So I added a couple of deuterium oxide, that is water, and the signal got sharper, and in some instances it disappeared. All right, that told me that it was interchanging with the chloroform. So this is what a typical technique we usually do to determine if there's a free or labile heteroatom there. So acidic protons, proton exchange, hydrogen bonding in NMR. So X and Y are electronegative. All right. Like example, oxygen or nitrogen or even a halogen. The interaction is electrostatic. So there's a charge distribution as a result. So you have a delta negative, delta positive, delta negative. All right, with the hydrogen bonding. So the hydrogen atom becomes more positive, X and Y become more negative, and in the NMR, the hydrogens tend to be more de-sheeted as a result in this proton exchange. Now, I should point out though that for alcohols, amines, and thiols, don't have in your mind that all alcohols come up at 3.97. Because I know you probably think that. It can come up anywhere. It depends on the solvents. So in chloroform might come up 3.97, in DMSA might come up somewhere else. And just because in this particular compound it came up at 3.97 doesn't mean for another one it's going to come up at 3.97. You understand? I don't want to think in your head say all alcohols going to come up at 3.97. It's not the case. All right? It can come up anywhere. It just depends on interaction. So don't be shocked if you see an alcohol broad peak come up around 4. All right? Cool. You'll soon see it. And you have some instances can come up even at 12, but I'm going to show you that. Right, if I did it in neats, you have strong intermolecular hydrogen bonding, and in the proton comes up around 5.28. All right, neat. Means if I use it in, if I use a solvent, let's say I use a deuterated ethanol, run ethanol, it comes up at 5.28. You understand? Or OH in methanol and tetrachloromethane, it comes up 0.7. So you see that same OH comes up differently in different solvents. It can come up 5.28 or it can come out 0.7. So it just depends. All right, so this is talking about the intramolecular bonding. Now with carboxy, if you have like type of intramolecular bonding like this, these protons tend to come up around 12. So if you see a chemical signal for a proton around 12, you start to think like this. That means it's next door to an electronegative atom where hydrogen bonding can take place. It's next door to an electronegative atom that has a lone period and hydrogen bonding can take place if you see something come up at 12 ppm. So O-hydroxyacetophenone, you see a proton at 12 ppm if you run the sample. And the value change with dilution because it's just going to keep bonding with it. It's just that close. And remember, as one becomes, the closer it is, the more positive the proton becomes. That's why it's shielded so far down. All right. All right, so you guys can take a break. We start back at 1 o'clock. All right, so welcome back. So continuing last class, I should say lecture, a guide to proton NMR chemical shift. This is just to remind you guys that there's information online in various means. You can actually look for this. The link is supposed to be actually on it. You can actually Google this, a guide to proton NMR chemical shift values. All right. We're going to speak about spin-spin coupling today. Yeah, we'll have 2 more after this. Then we'll finish with proton and carbon NMR. NMR and carboxylic acids and amines. The tutorial is up with carboxylic acid and amines. The quiz is next week. You're breaking up. All right, so NMR chemical structure. There's 4 types of information from an NMR spectrum, makes it extremely valuable technique for determining a chemical structure. All right. The first thing, the number of set of peaks. Probably should write that down. The chemical shift, very important. The integration and the splitting. All this information can be used to put together the molecule that you've been assigned. All right. So the number of sets of peaks, this corresponds to the number of magnetically or chemically different types of proton. All right, if they're in different environments, you get different peaks. If they're in the same environment, you get the same number of peaks. Well, you get 1 peak if they're in the same environment. Everybody understand that? To determine the identity of the molecule. Because I will give you guys a spectra or some values and say, propose a structure of this compound. Yes. Yeah. There would only be 1 signal. The integration will tell you that there's that much of carbon, or that much of protons there. The integration. That's why I don't reach there yet. All right, so chemical shift. The key to NMR spectroscopy is that the exact energy at which a peak comes, which can be measured extremely accurately, is dependent on the local environment of the proton. We explained that at length last class, or last lecture. All right, the environment it is in gives you a specific chemical shift. So you can know what type of proton it is. So this means that you guys need to know the types of protons and the chemical shifts where they lie. The integration. The area of the peak is proportional to the number of protons that are magnetically equivalent. Means that for a specific chemical shift, the protons underneath, well, the number of protons underneath is for a specific chemical shift, right? And I'm going to give you examples as we move forward. Splitting. This is also very important. The splitting tells you the type of proton and how many protons are neighboring that proton. All right, that's it again. The splitting tells you the type of proton or protons that you're dealing with and how many protons are next door. Make sense? All right. You'll see in a shoe. Because as you see a signal, based on how it interacts, it will break down into smaller signals. All right. But you'll see what I mean. So the electrons in the molecule have a small magnetic field associated with them, which tends to oppose the applied field. We spoke about that in previous lecture. These magnetic fields can either screen or shield the nuclei from the full strength of the magnetic field that is being applied. The greater electron density, the greater the shielding will be. We spoke about at length that in the last lecture. Hence, the nuclei in which is an electron-rich environment will undergo transition to a higher applied field when the nuclei in poor environments. Thus, the relevant field at the nucleus, which determine the energy of the transition, now becomes, H effective equals to H applied plus H shielding. All right. Now, this obviously is going to be an opposite value from the applied field. All right. Go ahead. What are the units for these? Well, I'm guessing it would be, if it's magnetic fields, it was going to be hertz or any form of units like that. But I'll give examples, of course. All right. All right, so chemical shifts. Yeah. Right. Because just how the formula is written. Yeah. That's just the nature of it, right? So the because sometimes it can reinforce it, sometimes it can, but it's just plus. All right. Yeah. So it's not a bad question. So chemical shift. The resulting chemical shift in the NMR signal for a given nuclei is referred to as a chemical shift. For a proton, chemical shift is given relative to the absorption of tetramethylsilane, TMS. The chemical shift is in hertz, is proportional to the operating frequency, and is given by the chemical shift, this value. So the frequency of the proton minus the frequency of TMS. You have to have something to refer to, a starting point, a reference point, whatever. Chemical shifts are reported in a manner that is independent of the frequency. So the chemical shift, where we talk about, so the change in the frequency divided by the operating frequency times 10 to the 6 to give us in ppm. This equation is just a repeat from what was in lecture 12. All right. Now, in this scale, TMS is arbitrarily assigned as 0 because it's inert, it's very shielded compared to everything else. I just use 10 to the 6 to give it a scale of convenience, all right? So ppm. Now for proton NMR, the chemical shift, which is given by delta, generally extends between 0 and 12. That's why I will not give anything up to 20, but you have examples up to 20. I mean, each chemical inequivalent nucleus has its own chemical shift that is independent of the operating frequency of the NMR. All right. The ppm scale is plotted from delta equals 0 on the right, with increasingly de-shielded on the left. So right shielded, left de-shielded. Right shielded, left de-shielded. Right shielded, left de-shielded. So on the right you would have 0, on the left you would have 12. On the right 0. 12. Well, you see examples, all right? So electronegative groups are de-shielding against protons and carbons in the vicinity of electronegative atoms are de-shielded and appear at a higher chemical shift. The more electronegative groups, the further downfield the proton will be. All right? Right. De-shielded, downfield. So just remember DD, downfield, de-shielded. DD, like in Dexter's laboratory, DD the sister, de-shielded downfield. If you remember that, Upfield shielded is it's just a done deal. Done deal, DD. D shielded downfield. All right. All right. So in this example now, if we had to now assign the chemical, in this example, if we were to have to assign the chemical shifts, where would you put 1, 2, 3, and 4? What is that 0 again? Can anybody remind me? TMS. I don't see anybody assigning TMS. I would be very upset. TMS is 0. That's a reference point. So if anybody assigns 0, I would be upset. All right. Don't assign 0. So which one will correspond to this chemical system? I should do it like that. 1, 2, 3, 4. Which one? All right. All right, fine. Let's go to the highest then. Which one would correspond to this chemical shift? 3? Everybody agrees? Okay, why is it 3? Because I'm assuming it's you, Vanessa. This who says? It's the most de-shielded. So she said 3. She said 3 is the most de-shielded. All right. What about, yeah, she said, no, she's asking at 4, chemical shift of 4, right? Most one to the first to the left, which is the most de-shielded. She's saying it corresponds to carbon 3. All right, fine, I'll work with that for now. What about the one that's most shielded? Which one would this be corresponding to? 1. All right. You see how far 1 is from every electronegative group? So it should be the most shielded, right? Okay. What about 2? Where you expect 2 to be? This one, which one? This one? Yes, that will be number 2. And then, I'm sorry? Why? It is more de-shielded, it's closer to the oxygen than this one, but it's still a good distance away. So the effect is not so strong. All right. That means obviously that this one would be which one? 4. Was that so hard? Yes. Well, you don't know what's going on. All right. Let's start off from the start. All right. All right. The first one, if we're to assign, oh God, there is you. The first carbon, the first proton would be assigned as 1. All right. If I go to into split, you'd have seen it even more. It is the furthest away from any electronegative group, so it'll be the most. Don't answer Brittany I'm talking to. Good. Okay, good. So it will be the most. Is it downfield or upfield? D shielded downfield. So this is no upfield. You just said it's shielded. Okay. Remember D shielded downfield. Yes, Saunders. No, upfield is on the right. D shielded is on the left. So I need to say that again. Upfield is on the right. Upfield is on the right. D shielded on the left. 0 right, 12 left. This is my left. Oh, that's your right. This is my left. Sorry. This is my left. So I mean left. The reference point is here. That is 0. 0. And it's on your right, on the screen, on the screen, on the, sorry, on the screen, if I'm looking at this is my right. Like, oh no, that means this is left. That's the most de-shielded. I'm looking at it from my laptop perspective. Oh God. I'm just to know, but hold on. Technical difficulties. All right, so let me say it again. I'm not sure the confusion is coming from, but I don't give you a table yet. I just talking. No, I don't give you a chemical shifts yet. You know, I'm just talking to the general. Hold on. Hold on. Give me a second. The technology is being a bit difficult with me right now. Sorry. No, every time I use this. All right. So ready again. Ready again, myself. Well, you and Saunders are talking to. Unless anybody else have any questions, you can jump in. But everybody else keep quiet if you understand. I was talking to those who don't understand right now. So ask questions now. Everybody, if you understand, just keep. I want to hear from those who don't understand. So the first speak. So Brittany and Saunders right now, because nobody them don't understand. You don't understand. All right. So Brittany, Saunders, and James. All right. So pre-war one, right? We assign this as carbon as proton one, right? It's the furthest away, so it is the most. I said, another hearing problem. James, Brittany, and Saunders alone. It's the most shielded, so it's going to be upfield, right? Upfield. Cool. If that is the case, 2 must be the one next door to it. Notice the position where 2 is. 2 is close to the oxygen, but not close enough. Exactly. Well put, so not close enough to feel the full effect of the electron withdrawing effects of that oxygen. So it will be more de-shielded than 1, but less compared to the others. Does that make sense to you guys? Yeah, so forget that over the right. Yeah, the upfield. Length. See this up. The peaks. All right. So that's another good question. Now, as it splits, it's a one signal that it resonates it with, you know, it splits into smaller fragments based on the neighboring protons. Come close to it, but we don't reach there yet. So just give me a minute. We don't reach there yet. We'll talk about splitting and splitting pattern. All right. We just understand the chemical shifts just generally first. So that would mean that 3 would be the one at 4. All right. It's the closest to the oxygen, the most electron withdrawing. So it should be the most de-shielded and further to the left. Yeah. And more downfield. All right. So I can ask you questions like this, you know, de-shielded, downfield. I can ask you, this is chemical shift, de-shielded and more upfield. I could put it as a result, as a response to a multiple choice. So you have to know the difference. Upfield, downfield, de-shielded. So upfield shielded, closer to 0. Downfield de-shielded, closer to 12. Just remember DD. Downfield, de-shielded. If you can remember DD, everything else makes sense. Remember, with those swap, we just understand something, I will run with what we understand. We're getting confused. How much time must say it? All right, we'll say it again. D shielded, downfield, closer to 12. Upfield, shielded, closer to 0. There should be no confusion. Okay, I don't know where they said they're hearing something else. I don't know if I'm saying it without realizing it. All right, so 4 would automatically be the alpha protons, all right? It's the same component I give it back. You know, so just extend it by 2 carbons. Okay. Why we don't use what? That's a good question. If there's no protons there, it won't give a proton signal. That comes into a part when we talk about the splitting. So you guys are asking, I'm really impressed. You guys are asking all excellent questions this time around. I don't know. I don't know if what is if in the catch up vibe for chemistry now. All right. Wait, I'm not hearing you. So the question again? The one above, yeah, the one attached though. Is this not clear? This is 3? That's not clear? All right. So we're now on anisotropic effect. All right. All right, so some chemical shifts are not predictable by the electronegativity or hybridization effect. So let's look on what we're talking about. So you have ethane, ethene, and ethyne. Now we would anticipate that the guys, I need your undivided attention. The talking supposed to be talking to. All right, so the anisotropic effect. Some chemical shifts are not predictable from the electronegativity of and the hybridization effect. So let's talk about this now. All right. Ethane, ethene, ethyne. We anticipate as you more move towards the S character, the electron withdrawing effect should be greater, right? And because typically this would allow for ethynes, or I should say alkynes, to be acidic, that terminal proton to be acidic because of its whole electron withdrawing effect. But notice that the chemical shift here is lower than that of the ethane. Now, how do you explain this? Due to anisotropic effect, all right? So these technology, channel star. So these hydrogens are acidic and bear the least electron density. We know that from our chemistry from last semester. These are facts, good times, right? They appear at seemingly anomalous positions on the NMR scale. Upfield, shielded, and this is due to what is called the anisotropic effect of the C triple bond C. Now, when we talk about anisotropy, we talk about non-uniform distribution of magnetic field within a molecule. We talk about anisotropy, we talk about non-uniform distribution of a magnetic field within a molecule. When we talk about anisotropy, we talk about non-uniform distribution of magnetic fields within a molecule. Sorry? It's an anomaly, but you can explain it. So I could ask you guys this question, I could give this right back and say, explain the anomaly of why ethyne comes up at a chemical shift of 2.3 while ethene and ethane comes at 0.9 and 5 points respectively. That's a good question. But then you'd have to say it's an anisotropic effect and then explain what it is and draw the diagram I'm going to show you next. All right. So the pi system of alkenes in aromatic compounds and carbon is strongly de-shields attached protons and move them downfield to give them a higher chemical shift value, delta value. Let's look what is going on. This is a magnetic field, right? The electrons are moving in such a way that it adds to the proton near to this. All right. So the electrons are moving. circulating electrons. So this is the movement of the nuclei spinning. Now the electrons here within the molecule are spinning in a counter direction. So it adds to the overall value of the applied field. Basically, it's how should I say this? It reinforces the de-shielding effect of the magnetic field, basically, how it is set up. All right, making it more downfield as a result. So the electron circulation is stronger in some orientations of the molecule in the magnetic field than others. And interaction is called the anisotropic effect. All right. So it reinforces the de-shielding effect, causing it to be more de-shielded than it would intend to be. Now, in this instance now, in the alkyne, it reinforces it goes against it. It pulls away from the magnetic field of the overall effective magnetic field that is experienced of the compound is decreased because it goes against it. That's why you expect it to be more shielded. Remember, we spoke about it, you know, the secondary magnetic field that is going to be deduced. For it to be de-shielded, we spoke about electron density being removed. But if it enforces a magnetic field that is already there, that it does in alkenes and aromatic rings, it can cause it to become more de-shielded. It's just that this effect is more pronounced in benzene rings than in alkenes. So that's why benzene rings now come up around 7 to 8. Alkenes come up between 5 to 6, but alkynes, because the secondary magnetic field opposes it, means that it protects the nuclei at more electron density, it causes it to become more shielded as a result. Does that make sense to you guys? Okay, good. You guys got that easier than I expected. That's good. And then I talk and you just jump out. No, I said the benzene ring reinforces, all right, the spinning. So it will precess or spin at a higher frequency and become more de-shielded as a result. All right. It not oppose, it will reinforce because alkyne, right? It opposes it. So it will now spin at a lower frequency, becoming more shielded as a result. Went to arts. So the pi bonds are going to bonding with ethine. The pi bonds form a cylinder about which electrons to circulate. So the electrons in circulation are like this. So when the C triple bond is parallel to applied field, the induced secondary magnetic field opposes the applied magnetic field in the vicinity of the protons. So it means it opposes, so the effective magnetic field that is felt by these protons decreases and make it more shielded as a result. So that's why alkynes, protons are shielded as a result of the anisotropic effect. Now this doesn't stops at alkynes, alkenes, and aromatic rings. It also extends to carbonyl systems. Because typically, oh Lord. All right. Yeah, this is just one lecture. So the carbonyl peaks, that CO bond as well. So look on the aldehydic. This is called the aldehydic proton. They typically come up approximately 9 ppm. Aldehydic protons typically come up around 9 ppm. The aldehydic protons typically come up around 9 ppm. The aldehydic protons typically come up around 9 ppm. All right. And it appears much lower than predicted using electronegativity, because typically you'd say that you'd expect it to come up around 2 or 3, right? But because it's directly attached to the carbonyl group, the carbon is, remember, it's trigonal planar, so it's flat in a plane, right? When the carbon double bond is oriented in the magnetic field with the plane of the trigonal carbon, to the applied field, the secondary induced magnetic field reinforces, doesn't go against it, reinforces the applied field in the vicinity of the aldehydic proton. So see right here, it reinforces it. So if it reinforces it, that means it's going to become more de-shielded than usual. So it's going to spin at a higher frequency. All right. And as a result, it becomes more de-shielded by the anisotropic effect. All right. Do I need to go through benzene now? It's the same principle. So I'm going to skip over it. All right. Same thing. The secondary magnetic field reinforces the applied magnetic field. So it becomes more de-shielded. All right. So that's why it typically comes around 7 ppm, 7 to 8 ppm. All right. Now, here's just a general trend. This should be your best friend. This little general trend table should be your best. You can ignore it if you want to. I wouldn't recommend it though, but it should be your best friend because it tells you, gives you an idea of how things are supposed to come. All right. If they fall out within a general range, it tells you something else is happening. For example, if you see a benzene ring, I see the chemical shift closer to 6, like say that it comes out of the 7 region and come like 6.5, 6.4, 6.8. What does that tell you about that ring? Remember the remember the base area, the typical area is between 7 and 8. If you see something between coming out of the 7 region, let's say it's closer to 7 and it's moved to like 6.9, 6.8. What does that tell you about the benzene? It's shielded. So what type of group would be on it? No, what type of group? An donating group would be weak or strong? Strong. No, can you say weak? Don't say weak. If I say coming out of the 7 going to the 6, that means it must be strong. So you're thinking about what type of things, like your amines, your alcohols. Remember we spoke about activating groups and deactivating groups in aromatic kind of member? I need a vacation. Yes, it is. Anything with lone pairs that can add to the ring are activating groups. All right. All right. So I know I'm gonna write that down, but okay. If I see something in 7 to 8 region and I see it now moving closer to the 8 and going to like 8.2, 8.3, what type of group is on the ring? Deactivating, right? And you could give an example of a strong deactivating. I know it too, or like a nitrile. You understand? So you should think about these things. When you see something outside of a region, you should first know what the region is. So when you look up the NMR tables, first thing you need to do is record the general region is. So right, hold on, I'm finish first, I don't want to lose my train of thought. So you write the general region for alkanes, alkenes, alkynes, alcohols, amines, esters, carboxylic acids. When you see it now fall out of that region, it tells you that something is there. It's either an activating group, a deactivating group is there. You understand? A shielding group or a de-shielding group is there. That is how you learn this. Don't sit down and say, oh God, all these things back for learn. No. Use your mind. Do it smart. Know the general areas, then you can understand where it comes out of that area to recognize that trend. This is how you do science. Look for trends. Everybody understand that? I'm giving you guys liquid gold here, Yes, Judith, what your question is now? They're deactivating. So, all right, so that's a very good question. All right, so that's a very good question, Judith. So you have some instances where they play as both, meaning that they can activate the ring through resonance, but deactivate the ring through induction. So sometimes both effects can take place. All right, Judith? So you have to just look on the chemical shifts and then determine which one is taking its effect. And if you can reason it out and it makes sense, I'll give you the mark. But if you give me full, you know, say it wrong. Oh, you know, that's why the tutorials are there. The tutorials. You have a tutorial this week. A means an NMR. You look on the tutorial. It's posted from Sunday. Yesterday, Sunday. All right, so integration. Wow, I'm almost out of time. One further feature of the proton NMR is the fact that the intensity of the absorbance can be determined based on the integration, right? All right, so I'm going to skip over all of this. So what this all is basically saying is proportional to the number of protons underneath the curve. That's what all of this paragraph is saying. The integrations are typically given as whole number ratios. Now, I could give you an integration as fractions or as decimal points. What you do is to find the what? The empirical formula of it, right? So you just divide through by the lowest value, and whatever you get as 1, you use that as a reference point to everything else. If I give you a set of fractions for integrations in a spectrum, right? You look for the lowest value, you divide through all integration by the lowest value, and that gives you everything with reference to the lowest value. All right. So if something is 0.1, you have 0.4, 0.5, 0.7. If I divide through by 0.1, you have 1, 4, 5, 7. You understand? All right, I need to check it again, but I'm almost sure I've uploaded it. So terbutyl methyl ether will also have 2 peaks in the proton NMR, one at 1, area of 3, and a second one at 3.5 at area of 1. Relative areas of our both peak are the same, but one represents 3 and other represents 2. So let me just show that graphically. So remember, we're talking terbutyl methyl ether. All right. What is this? Sorry. Terbutyl methyl ether, right? How many chemical signals are you expecting to see here? 2. You see the 2? How many chemical signals are you expecting to see here? They said 2. You see the 2? Each of those methyl groups on a terbutyl are the same. But you could see 1. These will come up as 3 protons, and this will come up as 1. Now, obviously, that don't make any sense, right? Because there's more than that. But if you know a methyl group, if you see a methyl, let me finish what I said. If you see a methyl group has 3 protons, that means you have to multiply this by 3. So this is times 3. That makes more sense, right? So if this is 3, that means this is 9. You understand? This is a CH3. We're talking about integration. You may not always get it as the same ratio as it actually is. So you have to know what type of groups it is. You understand? So if I know it's a methyl group and I say integration of 1 to 3, I know a methyl group don't have 1 proton. Right. We're talking about integration. The number of protons that is underneath a chemical shape. Because I could give you something like this, 1 proton. A methyl group don't have 1 proton. That's just insane. So it means that if this is 1 and each methyl group has 3, that means the terbutyl must have 3 times the methyl group, so it must have 9. You have to know. Don't worry, we'll give an example. All right, so ethanol, how many peaks? 2, 3. All right, 3 peaks. All right, so we need to talk about equivalence now. Don't worry, we're almost finished. We just have 15 minutes left. I'll give you guys an additional 5 minutes if you guys have asked me any question. I don't know why. I'm still hoping, call me a dreamer. I'm dreaming that you guys will just line up and say, I have these questions, or I did these questions. I want your opinion. But I know that it's going to be exam time, right? So equivalence. Now, if we were to place this hydrogen with a different atom or group, they will be in a different environment, right? First of all, they're all in the same environment here, correct? If I replace this with a chlorine, now this is a different environment. So it means they're not chemically equivalent to one another. All right. But even if I do put in a different position, they're still chemically equivalent. Okay. These are called homotypic hydrogens. All right. Now, if we replace H with a different atom or group, in this instance, this now becomes chiral. So these are called enantiotypic hydrogens. Enantiotypic means that if I change one of them, it becomes an enantiomer of the other. They're now enantiotypic hydrogens. The chemical shifts are the protons are in the same chemical environment and they will have the same chemical shift. All right. But there are different types of hydrogens. One is homotypic, one is enantiotypic. Enantiotypic. But that's what I'm saying. They will be the same environment. They have the same chemical shift. One is R, one is S. You seen it? It's on overlay. You can see it on your screen. This is not chiral. This is not chiral. This is chiral. When I switch it with something else, it becomes chiral. It's not the same structure. One is out of methyl group where the hydrogen is. All right. You don't need to work it to see. I don't know how to if it's R or S. Just if you see 4 points of attachment, automatically it's supposed to spring in your head chiral. So you know one is enantiotypic, one is homotypic. All right. I won't ask to RS because I'm assuming after the tremendous testing I did last semester that I don't know what chirality is. I'm gonna shell the exam, so unless somebody cheat. Equivalence. Now, if we have this, we identify this as a stereocenter, right? And replace one of the red hydrogen with a different atom or group. With the chlorine, same thing with the blue hydrogen. We have RS, RR. These are now called diastereomic hydrogens or diastereotopic hydrogens. Yes, the stereochemistry has been back. It's been back right now. It's coming right back. All right. The two molecules, both created, will be diastereomers to each other. In principle, these two hydrogens should have different chemical shifts, but they typically tend to have the same. So spin-spin coupling, splitting. This is where we talk about splitting. Let us consider diethyl-ethyl. How many peaks would this have? 2. Good. It's only saying that with confidence without thinking. 2. This is how it would look. Which one would be? This is called a methylene. All right. That's a CH2. Which one would correspond to the methylene? Okay, that's correct. So easy that was? You look like you're hesitating to say yes. There's not a trick question, you know. I'm sorry? Really? Oh no, I cut that part out. But you know, TMS comes up at 0, right? Sometimes it can really and truly shouldn't have, but sometimes it boils off out of the solvent, but it really should be there. But you know, it's not it. Well, it's not TMS because TMS is at 0. What was the question? I'm lost in thought. Remind me the question. One is furthest away from the oxygen will be the most shielded one. All right. Right. So this would be the CH3. This would be the CH2, also called methylene hydrogen. CH2 are described as methylene hydrogens. CH2s are described as methylene hydrogens. CH2s described as methylene hydrogens. All right, so the NMR spectrum has 2 sets of peaks, one with 4 lines of relative intensity of 1 to 3 to 3 to 1, which total integrates for 2 protons, and one set with 3 lines with intensity 1 to 2 to 1, which integrates for 3 protons. All right. This is what we're talking about, splitting. I know you can recognize splitting patterns. The multiplicity is due to a phenomenon known as spin-spin coupling, and it arises because of the interactions of protons among the protons in the magnetic field. All right, mediated by the bonding electron. So let us consider this: XCHA, CHP, Y2. Each proton has a spin half, and there are equal probability of its spin being aligned with or against a applied magnetic field. Does that make sense? Ooh. Almost finished though, you know. All right, I'll end the class now, and then you guys just go through this and do the tutorial. All right.